Hello friends, welcome back. This is week 7 and till now we have understood about the basics of 3D printing. We discussed about the fundamental part and we explored the polymer, metal, gel based 3D printing. We also discussed about the fabrication of the sensors. Now in this week we will see how our previous knowledge will help us to develop a actual product. So these are some of the case studies in this week we will see that has been done at NITTTR Chandigarh. The special focus is on the development of the product for the veterinary patient, and we will be talking about the different aspect in orthopedic and dentistry application. So all product that has been developed, these are in-house and the IPR is lying with NITTTR Chandigarh. So specifically some of the studies at Chandigarh. So this is one of the first case study that I am going to discuss with you in this week. This is regarding the development of innovative intermedullary pin profile for canine with DMLS oblique FDM. Canine is basically dogs family that we are targeting, and the technology that is metal printing, direct metal laser sintering that we have in our place, and fused deposition molding for making the polymer part. The problem is actually for the small dogs, puppies, normally 3 to 4 months. Now, just common example is like falling from some height or because of some vehicular accident, there can be a bone fracture over here. And as a standard procedure, what we will do, we insert a pin into it. We call it as an intermedullary cavity, and the pin is called intermedullary pin. For this age group of puppies, normally this pin has to be inserted for 10 to 12 days and there is a healing. After that, we normally remove the pin. Now, the point is from this side we insert, we call it as a proximal end, and from this downside, that is a distal end, this pin is inserted. Like when we see this type of cases in actual environment, what we observed, the standard pins which are normally taper that are being inserted into this, they have one common problem, like because of the galloping that by the dog, this pin comes out from the distal end. So this pierce actually the all soft tissues and all. So we need to perform a surgery immediately, and the pin has to be removed, as well as the whole blood loss and lot of pain. These type of problems are being observed by the patient. Now the point is, if I can increase the retention period of this pin, and this pin doesn't come out from the distal end, this will be a great help to the veterinary surgeon. Now if we see the bone part, as you can see in this picture, if I insert a pin from here, the zone here, the dia is typically reduced to the 70%. So what the collaborator with me, Professor Ashwini, who is the veterinary surgeon who actually performed the clinical trial for us in this regard, the suggestion from the surgeon was, like, if somehow if I can increase the retention at the proximal end as well as at the distal end, then this can be improved. So what we did is we selected a typical profile of the screw threads that we learn in our first year of engineering and all. So for the load bearing capacity, using a square thread, and for the interlocking using a V thread. So we tried the different profiles, and these were printed on a typical polymer printer, right, using a fused filament fabrication or fused deposition modeling. And then once the different designs were approved, like this is the final dimension and the drawings that has been approved by the surgeon after wetting is on the polymer part, the final component was prepared on a metal 3D printer, and then these are being inserted into the actual patient. Normally, the length requirement is typically around 19 centimeter. So this can be typically prepared in our lab. So we were able to develop the product using our polymer printing and gel printing, and then doing the assembly. So now this study that is in front of you, this is the extension of our previous work. Here what we want to do is, we want to see the effect of metastructure on this actually pin. So here the idea was to replace the metal pin with a polymer pin, and the material selected was PVDF because of its piezo property, and the intermodular pin for the typical 4D application was given the metastructure like 50% in the middle, 40% in the middle, 30% in the middle. Basically, this metastructure help to have typical, shock absorbing capacity for the pin. So this study is basically on the design, fabrication, and destructive testing. We explored the tensile part, compressive part to mimic the actual loading condition in the canine. So this novel intermodular pin is of course biocompatible, and it may not be required to be removed. So by using a metastructure in the 30% range, 40% range, and 50% range of PVDF, we were able to get really good results. So again, the higher metastructure is better. So finally, the 50% zone with the meta range is recommended in this case. So all has been prepared in house using our own lab scale printer. Now this is the another case study that has been put for the dog. Specifically, this is for the defense dog. In typical canine case, which is basically a dog family, we have a combination of 48 tooth. Like in case of human, we are having around 32. Here we are having the case with the 48 tooth. Now out of these 48, the 8 are considered to be the strategic one. Like you can see, this is the maxillary arc, this is the mandible, and in maxillary and mandible we have a combination of 8 tooth which are considered to be strategic. Like this is the canine one, this is the maxilla PM4, this is mandible PM1, which is actually considered to be the strategic one. So what we actually did in this case study was perform the pre and post processing using a metal printing part, as well as the sacrificial pattern was prepared by the ABS polymer, and which was used for the investment casting. So all typical CAD designing and then fabrication of the polymer part, and then making the crown, and here is actually the assembled part into the actual canine. So you see, this is the damage part, specifically the canine one and the PM4 one, and these are the typical crowns that has been prepared, and the typical all dimensional part and assembly feature into the actual installed into the dog. Here the typical idea is like we have a concept of interchangeability present naturally in these type of canine family. Like normally in this zone we have around 8 breeds which are commonly being used as a guard dogs, and let us say I am using a German Shepherd or Pit Bull 3-year male. So all animals of same breed, same gender, same age will have almost the similar dimension. This is unlike in case of humans. So we have a lot of interchangeability, and we can think of making it as a batch production and can be used for the trained dogs in typical defense or policing applications, right? Now this is the another case study for the development of the partial dentures using 3D printing. So we can have a polymer based master pattern, then some chemical vapor smoothing is applied over it. So you can see the polymer part after the chemical vapor smoothing is basically improving the surface features. Right here, STL file formation, printing on the actual printing on the polymer printer, and this is the typical ABS pattern, typical bridge shape specimen have been prepared. Now this is the standard assembly process. Like there is a tree formation, then making a investment pouring, then investment actually poured into the cavity over here, and then investment ready, then cavity for the casting is there, baking of the investment using the induction casting setup, then denture actually prepared, and this is the final product that can be used for installation into the any patient, right? So this all prepared in house at our lab. This is a typical example of making a implant. Right now, till whatever we have observed for the dentistry application, was for making a crowns. Now here the next stage is basically to develop a implant, right? So this is a implant that has been developed with the collaborators from the dental hospital, Dr. Jain. So the IPR is with our lab. So in this case, we develop some low-cost indigenous 3D printed hybrid dental implants, and this is in 5 parts along with the armamentarium. This can be a typical contribution from the manufacturing domain to the surgeon. Like along with making a implant, we are also supplying the armamentarium part. Like the sometimes the components are so small to hold it and to install it into the some cavity, some special armamentariums are required. So all has been prepared in this case study by using a metal printing in our lab, and these are the typical parts over here. If I just give an overview, this part goes to the socket. Now then there is a protruded section. Now this part, which is in the form of some meshy structure to the tune of 10 microns, this is basically installed for the secondary stability, and then here the top over here, and on this there will be abutment, and finally the crowns will be placed over here. Now to make such component with very small size, all armamentarium and all dimensional part that has been prepared at our lab. Now this is again the extension of the same work. This is the typical work for German Shepherd. Here the strategic tooth implant has been prepared, and in this case there are 3 routes. Now the typical application is, like in this case the load application is to the tune of 800 Newton, whereas in case of human normally doesn't go above 80 Newton. So here it can be typically 800 or 1000 Newton. So natural phenomena is the more number of roots are there, as you can see. So all these roots have been 3D printed and installed along with all the armamentarium. The again the IPR live with us. Now this is the next case study that I want to show you for the development of the orthopedic part. This is the typical hip joint, and for the hip replacement I am interested to develop some of the benchmarks, as you can see on this screen, of different dimension along with the collaborator. So like in typical casting study, what we do is we develop a pouring basin, then have a down sprue, then the links and gates are there, right? So along with this the different polymer part that has been prepared by fused filament fabrication, those were attached to it, and there are the standard, this is the sprue, here are the patterns attached, and then I am putting a molten wax coating around it to give it a smooth finish. Then the slurry coating around it, like a typical investment casting process, and then removal of the polymer part. Here one of the negative part or the disadvantage is to remove the polymer, which was ABS in this case. I have to raise the temperature above 1050, whereas if I use it for wax, this will be maximum up to 182 or 200 degrees Celsius, right? So after that cavity is created, then putting a stainless steel 316L or stainless steel 304 as per the requirement, these benchmark have been prepared. So typical commercial application for developing the in-house these type of the hip joints is very much possible in-house in our lab. Now this is another case study which involves all the processes that we have seen for the solution of the hernia in case of the cows. Specifically, we have the target for the abundant cattle. So the idea is to help the patient for the abdominal hernia. So you can see, as in this picture, there is a uncontrolled growth of some tissues. So we can see this is the abdominal hernia in cow. Now what I have to do is I have to cut this tissue, right? So after the surgery we put the polypropylene mesh over here. Normally, the life of these type of animals is around 8 to 12 years, and the life of this type of the mesh that we use is normally more than 30 years. So there is no problem of using these type of meshes over here. So what actually we have done is to have a fast recovery of the patient, and for better wound healing, from the literature, we prepared a polypropylene with a reinforcement of CaCO3 in the form of the composite. So you can see that the composite has been prepared. Like in my second week, I talked about development of the in-house material, in-house filaments, and then in third week, we also discussed about the development of the feedstock filament, which has been prepared, and now using our in-house developed filament, which will be having a polypropylene as a major matrix with a reinforcement of CaCO3, which is basically a limestone. Because this combination gives a better wound healing, so we prepared this mesh and has been installed over here, and we got really good results because no commercial solution is having this combination. Only we are using the polypropylene mesh. So this helps basically in fast wound healing of these type of the patients. Okay, this is the another case study performed on the cattle itself. This is a typical hernia problem in case of the buffaloes with the high milk yield. Like one of the common breed that we see in our place is Murrah, and this is a very common problem with these type of buffaloes. Typically, these are called bubbleless bubbles as a scientific name. So what the problem is, like if these type of cattles go for open grazing, sometimes these type of metallic pin, they actually enter into the stomach part. If I see the typically the food pipe zone, so the food enters into this food pipe, and it goes to the one section which is considered as the zone 1, and this is called the rumen, right? So whatever the part, metallic part, if it comes through the food pipe, it goes to the rumen. Then from the rumen it goes to the zone 2, which is called the reticulum. Now this reticulum is having a honeycomb structure, right? So whatever the metal part will be there, it will just get stuck into here, this zone. Then after this reticulum, it goes to the zone 3, which is on the other side of the stomach, which we call as the omasum. And then after this, it goes to the zone 4, which is called the abomasum. So the major problem is in the reticulum zone, where my metallic part, foreign element, basically insert into this. Now the problem is, once there is a pregnancy of these type of animals, or you have a overeating by the patient, there will be extra pressure on this, so due to which the metal part that has been stuck over here, it actually pierce the this diaphragm zone, and next to this zone there is a lung part and the heart part. So the patient is having a lot of pain, and this may go to the cases of 75% death cases have been reported for such type of patient. Now to understand this problem, right? So what we have done is we have developed a innovative sensor, which is based on the concept of microstrip patch antenna. I will show you in detail over here. Like we have seen the food part coming to the reticulum. Now we develop a sensor over here, and this sensor part is installed over here at the diaphragm section. So this actually gives me the signal, if there is a excessive pressure, the radio frequency waves, the signal that I am getting is basically being captured through the Wi-Fi module or through the Bluetooth receiver, and my owner, or the surgeon, is getting a real time monitoring of what is actually happening at the patient end, right? So that is the beauty. Through 3D printing we are able to make a conformal sensor which actually take the shape of the contour and give me the real time data. So technically I am able to develop a digital twin of my patient for the online health monitoring. Now we can see the ultrasonography of these type of diaphragm, where the human reticulum part or any other foreign element we can also see in the X-ray imaging. So in the by the radiographic image we can see these type of metallic element that are coming. So we have to go for surgery. Typically, pneumotomy we have to perform. There are some symptoms that are given by the patient itself. So the diaphragmatic hernia typical signals are like there is a tympani, there is a edema, then persistent cough can be there, anorexia can be there. So there can be difficulty in breathing, weakening of the diaphragm, and diarrhea in some of the patients have been observed. And what we have to do is perform the surgery over here. Now the actual contribution from the mechanical manufacturing side is now to print the sensor if there is a case reported for such type of patient. So depending upon the site of damage, I have to develop a CAD model, converting it to the CAD file, generating the G code, then sending file to the printer, then print setup like fabrication. Like so we use again the polymer printing as well as the metal printing. As you can see, we have already discussed their schematic number of times. So in the medical field, we are typically using it for the anatomical application, medical apparatus formation, tissue engineering, making some surgical device. So the same thing has been used over here. So, what actually the procedure followed is like selection of the subject, collection of data, then sensor design using a HFSS, building a CAD file, selection of the material, then FE analysis using the ANSYS. Then, like we have seen this SAR analysis in our previous week for development of the sensor. Then, actually 3D printing the component, some part on metal printer, some part on polymer printer, doing some post processing, doing the characterization, and finally going for the implantation or the surgery. So this is the typical sensor part that has been developed for these type of patient. The IPR for this lies with us. So we have a typical ground plane and the conducting patch. This is a mesh type structure which was assembled, and the typical FE analysis was performed for all the different parts so that we can understand that there is not any failure in a uh, acceptable factor of safety. We have a damage life analysis of the assembly. We have biaxial indication analysis, and then the FEA one. For one stage of FEA we use the ANSYS, and then we use the 3D expert software which was provided by the company as a inbuilt software for the boundary distortion analysis and for the residual stress analysis. And you can see whatever the analysis we performed, the component designed by us lies within the limit. This is a typical G code generation and the parameter used for printing of the polymer parts. So for this typical application, infill density, raster angle, nozzle temperature, bed temperature were selected based upon the experimentation. Then the sensor was designed and fabricated using HFSS, and final fabrication using polymer printing. And we try to see the effect of fat, skin, and muscle, different type of tissues on their relative permittivity, then conductivity, mass density, and finally the SAR value. Then the return loss S11 values were also explored. Then before using it into the actual patient, the in vitro analysis was performed. So we try to see the effect of this foreign material, like for metal part we are using 17.4 pH stainless steel, for let us say polymer part using PVDF, and we try to compare it with the natural diaphragm. Similarly, the SEM analysis for the typical surface characteristics were performed, and the hardness for my part, fabricated part, and natural fellow diaphragm were also there. Then for actual fabrication, the DSC analysis, their wear behavior, their mechanical properties, as you can see in the screen, their morphological behavior, their EDS, their average grain size, porosity, these type of data that we learned in our previous all weeks actually being implemented. And as you can see, the result of the DSC, their tribological behavior, their in vitro are very well in the limit. Like you can see, the corrosion rate comes out to be 0.00259 mm per year, and in case of natural sample, the that is the buffalo sample, it is much lower, that is 0.000129. This is being observed from the TEFL plots, specifically in the in vitro analysis. Then the mechanical testing was also done. So it has been observed that the average yield strength of the diaphragm sample was 1.35 megapascal with a strain rate of 59.50%. And whereas for the metal part, the of course the strength was much more. We are having a 540 megapascal, and the yield strain was around 25%. Additionally, the hardness for natural diaphragm was also observed, as well as it has been compared, as you can see on the screen, for the polymer and the metal part, as well as for the natural diaphragm part. Finally, we were able to fabricate a sensor and see the result in the real time environment. And these smart sensor have a good factor of safety, and this was load for 10 is power 8 cycles for the boundary distortion. Similarly, for the morphological part, we are interested to see the porosity and grain size number, which were of course very well in the limit. And then the same data has been compared with the natural diaphragm. Then as regard to the thermal analysis, using the DSC, no deformation was observed. Right. So there are some limitation in this study, like we basically want to explore the metastructure, which can help me in having a better conformal size. Then the sensor, since I have to play at very low voltage, so to get it into the ISM band, of course, is a challenge. Then in this case, the PVDF composite was used. We can think of many more biocompatible, biodegradable sensor material. So we have used the PVDF composite mesh structure. We can think of making some composite which can give me better healing rate. And finally, the digital twin with a actual real model that can also help me in getting a digital ROM along with the real time data. Okay, so friends, this is the last case study that I want to discuss with you in this week. This is regarding the 3D printing of the stifle prosthesis for the patella luxation in canine. Again, the patella luxation is very common problem. This is just the overview. This is the natural bone. This is the tricular groove, and in this tricular groove, this patella bone actually slides, right. Now the problem is sometimes this tricular groove walls are damaged. So what I have to do is to generate these type of walls and allow the movement of this patella within this race. Now if it moves left or right, there is a big challenge for patient to move, right. So the actual practice was to generate a cage like structure over here. As you can see in different stages over here, different dimension cages have been prepared and assembled. Like this is the one of the typical part. Here we use the metal part and the polymer part, which is sliding into this, and we develop a microstrip patch antenna based sensor, and we try to see if it slides within this range. So what is the resonant frequency, and if it moves left or right, what is the change in the resonant frequency, right? So this case study is about this. So for the beginners who are actually not knowing the patellar luxation problem, you can see this is the patella. Now the luxation is like if this patella is basically the name of the bone. If it moves to this side, we call it as a medial patellar luxation, right? This is because of the deformation of the tricular grooves. And if it moves on the other side, right to this, is called the lateral patellar luxation. This is maybe because of the tightness and the looseness of the patellar ligament, right? So there can be bidirectional patellar luxation also. So in some time the patella luxate to the left, or it may luxate to the right. Now the researchers have developed the different grades. Like in normal position, this angle is around 90. So if it adds around 5 degree to one side, but less than 6, they call it as a grade 1. Then grade 2 with let us say between 8 to 15, then with grade 3 around 15 to 30, then with grade 4 more than 30 and less than 60, right? So accordingly the surgeon will take a decision for replacement, or making some cage for this. Now you see the actual problem is for the different age group of canine and different breeds, I have to make so many cages. So what we have done in this case study at our lab was making a one general purpose cage, which can be expanded. So it is expandable depending upon the size of the or the dimension of the bone. So through reverse engineering, develop a model. We go for the FE analysis, then we go for the residual stress and boundary distortion, fabrication of the component, followed by the morphological analysis, then thermal analysis using DSC, going for the wear testing, then going for the in vitro, then the porosity, grain size, roughness, etc., and finally a IoT based solution for the health monitoring. So this is the typical component I have explained already. The component was made in such a way like it can be put like a butt joint, and this is a this can be overlapped, so you can close it or you can open it, and then there is a race in between. Now basically I need a metal part, so this part was metal. So this is a insulator, which is a polymer, which has been inserted over here. Now to have a different age group and dimensional feature adjustment, so this part C that you can see, this is actually put at the different location, and finally assembly help me in getting a final product which can be installed in any age group. Only the replaceable part will be this part C, which can be adjusted and at which is of course very less cost as compared to rest of the parts. So this is the TI 6AL4B or stainless steel part, and this can be PVDF or PLA or any other biocompatible polymer part. So this is the assembled view, as you can see over here. So in this particular example, stainless steel for the metal and PLA for the strip and the moving part has been there. Then typically FE analysis, as you can see on the screen, then residual stress and the boundary distortion analysis, then fabrication of the part on the metal printer, as you can see on the screen. So the 3D expert software was used for basically the slicing. The parameter like laser power, layer thickness, scanning speed, hatch distance, then of course the energy density were fixed. This is a open source 3D printer, DMLS, which is basically a laser powder bed fusion and making the final component. Now this is the fabrication of the polymer part using the fused deposition modeling. So some of the parameters that we use for this, and these are the polymer parts that has been prepared, and this is the final assembly of the metal and the polymer part. Then going for its SEM and EDS analysis. Basically we are interested to see what is the you know composition, whether there is some impurity or some effect of the oxidation etc while processing. Then seeing the DSC analysis, basically I have to go for the autoclaving, and we want to see at autoclaving temperature the material is stable. Going for the wear testing, to ascertain that the sliding part, because that is the polymer one in this, what is the wear rate. Then seeing the porosity grain size before and after wear. Finally, like in our previous case study, going for the in vitro testing, seeing their porosity grain size before and after. Then the, of course, this is the FEA result. Then using the Guardian software, we try to see their surface roughness and the 3D rendered image. And finally, once all these parts are acceptable, then using a HFSS, like in previous case, we develop a sensor, as you can see over here, and then calculating the SAR values as per the law of the land, as per the required standard. It should be less than 1.6. So that has been observed in this case. So finally, this is the complete assembly, and this is the testing on the VNA for the lateral, for the medial pteralization case, and for the normal case I am getting a trend over here. So you can see the resonant frequency, the S11 values, these have been compared, and the results are within the acceptable limit. So we try to correlate this with the different mechanical properties. Dear friends, this is the end of the case study. So in this week we learned about different aspect of veterinary dentistry, veterinary orthopedic application, and we try to learn about the actual field use of our 3D printing technologies. So in our previous weeks, we have seen the fundamental of polymer, metal, gel printing, and here we actually implemented in some of the case studies. I hope the information was useful to you. And now in my last week, I will be covering mainly on the 4D part, in which we will be interested to develop some smart solution that can be actual used in the real world application. I believe that the information is useful to you, and so keep watching. Thank you very much.